Today I'd like to explore a powerful C++ feature added in the 17 standard, constexpr if. The main idea behind constexpr if is to have a way of conditionally branching at compile time. Let's get into some code. So here we are in Matt Godbolt's Compiler Explorer, one of my favorite tools. We'll be using x86-64 GCC with the C++20 standard today. Those of you familiar with the 23 standard may have figured out that I will not be covering const eval if. I will, however, be touching upon requires expressions since they do come into play a little bit later on. With our example here, you can see that we have a rather complex function for multiplication between a and b. You might run into something similar to this when working with C, especially in code bases where the code is meant to run on multiple platforms. Windows and a Unix operating system usually have different interfaces for their different functions. There are a few issues with this. We took two different syntaxes for if statements, and now they're together. We have a different syntax for the macros than we do a normal C++C if statement, which adds more complexity to reading the code and overall is not something we want. On top of that, we also have a macro, and macros have their own problems. You have to worry about multiple names, definitions, making sure they're not used in a wrong way because they're just put right into the text. It's not a nice solution, although it is a solution to this problem. Let's say we just want to go back to our normal syntax, where we have our nice if statement with the normal C and C++ syntax with our else. Now, I personally think that this is nicer, but it does come with an issue. Sometimes. The only issue it has is that the compiler might not do what it's doing right here. So you might notice the compiler here has decided, oh, can multiply is true, we're not going to worry about the rest of this. But if we make it so can multiply is not a constant, so we just have it as this integer, now we have to deal with all these different branches, which unfortunately is not something we want. So, how can we fix this? One thing we can do is just call this constexpr. It's a constexpr int can multiply, and we're back to where we were. This is perfectly fine, works the exact same, and I would recommend doing this over a macro. Macros aren't type safe, but this is. So, this is about something else though. This is about if constexpr. Now, in this scenario, it makes no difference to the output of our code. The compiler already knows it's a constant. It's already doing this optimization. Oh well. Now, the real power of if constexpr isn't for these trivial cases. It's for when you're using something like templates. So let's turn this into a template. Template. We're going to do a non-type template parameter here for can multiply. And we're just going to give a default value of true, just for the sake of it. Now you'll notice we have the exact same output, but we have something a little bit different that we can do with this code. So before, we were stuck with just having one of these implementations at a time, depending on that macro or constant expression. So let's say for some reason something happens and we can't multiply anymore. Some weird hardware issue. So we have to do the multiply with false. Unfortunate. Is this realistic? Not really, but it might happen. There are, of course, a lot of other scenarios where this would apply. So now we are getting both of the branches being compiled, but there's something a little bit different compared to if we were just using a non-const expression. So with the integer value that wasn't const expression, we did have the same amount being compiled, but the assembly was different. The thing I want to point out is that we have two separate definitions for my multiply in the assembly. One with the template parameter being true, one with it being false. The one up here represents our a times b, and that's being called here. And the other one represents this whole mess of the for loop doing the additions, and that's being used here. So these are same function name, just one different parameter, and they're completely two separate functions being compiled. Now, this is great. We've split the work, so now this won't be doing this comparison, and this one will also not be doing this comparison. And branching, it's not a huge overhead, but there is some potential overhead there that we are eliminating with this that we wouldn't be eliminating with just a simple Boolean parameter. Now, let's move into some optimization. O of 1. And as you can see, the compiler knows exactly what we're trying to do here, and it's great. We can just go straight to the result here. And if we really want to, we can even make this const expression. And it doesn't change anything, because the compiler is smart enough to know exactly what we're doing here. Now, one thing is we're doing something a little more complex here. This is much more complex. We are using all these templates and all these different things. We are starting by including type traits, IOStream, and string. Type traits is great, has tons of metaprogramming, useful little tidbits, little gadgets, very nice for metaprogramming. IOStream is just so we can output things. String is our string. So, little explanation of what we have here. We have a struct isMagic. It is a templated struct, and it is inheriting std_bool constant. Now, std_bool constant, the template parameter here, takes one Boolean. It's a non-type template parameter of Boolean. And then the struct has no real body. It's just really inheriting this bool constant. Now, you might have noticed requires, that's some C++20 nonsense, and you're right, it is. So, requires evaluates to a Boolean expression. What it really does is we have our statements inside of the curly brackets for requires. And if these statements are well formed, they are compiling statements, then it returns true and false otherwise. This is how we are checking if a type is magical. There's no deeper meaning to magic here. It's just a little example. And then we have a templated struct, which is magical. It takes a class type and it just holds that class type. It doesn't have any special operators or members on top of it, but it does have these two things. Magical things must be integral types, meaning integer, long, short, byte, unsigned, ints, all those good things. And it has a static constexpr auto called potency, which we're just assigning to size of t, which is a constant static expression. Now, with the magical struct, we can make magical values. So now here's the real thing I want to focus on, the if constexpr magic. So we have a constexpr long function called getPower. So it takes a templated const reference called creature. And by creature, it's just referring to anything. But the real thing that's going on here are these if constexprs. First, we check if it's a magical creature. If it is magical, we will return the creature's magic value plus its potency. If it's an integral, any integral type, so if it's not magical but it is integral, notice the else if constexpr, we're just returning that integral type, which is going to be an integer, a long, a short, and otherwise it's not magic, it's not integral, it's got a power of 0. Stood string, power of 0. How unfortunate. One thing though, is we do have an epic battle. Epic battle takes templated class A and B, and it does a battle. What we're really doing is just subtracting this get power for A and B. And we just return that, and then we have our main function. What is main doing? Not really anything important. We have a normal stood string called mundane string, and it's a smiley face. We have a magical int, which is a wizard int. It's super magical. And it has a value of 1. So we get the result of our epic battle between our string and our wizard int. And then we want to see who won and output what. So result of 0, they have the same attack power. Nothing, it's tied. Not very intense, not very fun. Now, we have result less than 0. The wizard won, because wizard is B, which means it'll be negative. And we will output the wizard won by the negative value of the result, because result is going to be negative in this case. Otherwise, the mundane being 1 by some amount, which probably shouldn't happen. So if we look at the get power in the assembly, this is where the nice thing occurs. We look here and here. We have, when we pass in our magical int, it determines that it is a magical value, and then it returns the creature's magic plus its potency, which we are doing here. Now, we also have the string version, which in the assembly is here, but is just this. in the non-assembly. Now, to prove to you that this is not real, it's not in here. The entire assembly, that integer, this integral branch, doesn't appear anywhere, which is something we want. Unless we had a mundane int. We'll leave it as a mundane string and just pretend it's not. Now you might have noticed this has changed. We're no longer returning 0, we're returning creature. And if we go to our assembly, we now have the magical variant and the get power variant of the function. Taking an int, we return just the creature, and with the magical, we return creature.magic plus the t.potency. Now, you may have noticed that I do have output for here open already. I'm going to make this large, and you're just using the default return 0 of int main. And the wizard int 1/4. Why is that? They both have the value of 1 as their .magic and their creature value, but size of int is 4 in this case, which is our potency. So, what if I were to have something else, like a long? Well, it does the exact same thing, except the wizard 1/8, since the size of long is going to be 8 in this case. Very nice. Now, you might have noticed we are in O0. No optimizations. Very sad. Very happy. O1 is cheating. They cheat. It's evil. It knows everything you're going to do before you do it. And it just knows the output's going to be 8. And then only does that. GCC is very smart. Way smarter than anyone could be. Back to our beautiful if constexpr though. Here's a place we can't do if constexpr. Why? Because result isn't a const expression. Not a const expression. It is just an auto, no const evaluation on it. Although the compiler is const evaluating it in this case with optimizations. And O of 3 super optimizations, it's about the same. It still has to output that, but it does a little bit of extra magic. O3 always does something odd. Very interesting. But yeah. So, that was a little look at if constexpr and a potential way to use it or use the type system to your advantage. Thank you for watching. Feel free to ask questions in the comments. The Godbolt links are provided in the description, and I hope this gives you some ideas on using constexpr if, and I hope you have a great day.